Rephrase it. ChatGPT said. ChatGPT. Dark holes, strange and seemingly infinite, contain masses many times that of the Sun, yet appear surprisingly small for such immense mass. Our own Milky Way galaxy revolves around a dark hole at the center, located in the Sagittarius constellation. Recently, scientists made an astonishing discovery at the core of these cosmic enigmas, revealing something both shocking and eerie that challenges everything we thought we knew about these celestial phenomena. According to Albert Einstein's theory of general relativity, dark holes have such intense gravity that not even light can escape them. Gravity, as described by Einstein, is not a force like magnetism or attraction. It's the result of how space and time are bent by objects with mass and energy. Imagine a massive object like a star. Its vast mass and energy cause a deep dent or warp in the fabric of space and time surrounding it. This curved space creates a gravitational field, and the greater the mass of the object, the stronger its gravitational pull and the deeper the dent. Dark holes are among the most extreme objects in the universe, with unimaginable amounts of mass and energy packed into an incredibly small space. This intense gravity creates an incredibly deep and powerful indentation in the fabric of reality. Near a dark hole, the gravitational force is so strong that it forms what's known as the event horizon. The event horizon isn't a physical wall. Space moves freely through and across it. This invisible boundary marks a point of no return. Once an object crosses it, whether it's a doomed spaceship or even light, it can never escape the dark hole's grasp. To emphasize how extraordinary this is, consider focusing a flashlight. Light travels at an astonishing speed of 300,000 kilometers per second. However, inside a dark hole, the speed needed to escape would exceed the speed of light, something deemed impossible according to our current understanding of physics. Once light enters a dark hole, it's trapped forever, unable to break free. Light coming from further away gets bent around the dark hole, forming the mysterious boundary known as the event horizon. This boundary isn't something you can touch or see. It's a mathematical concept showing where we can no longer observe what's happening. The size of the event horizon depends on the Schwarzschild radius, which is determined by the mass of the dark hole. The larger the mass of a dark hole, the greater its event horizon. Scientists use an equation, derived by astronomer Carl Schwarzschild in 1916, to calculate the radius of the event horizon. For example, a dark hole with a mass 10 times greater than that of our Sun would have an event horizon with a radius of about 30 kilometers. At the heart of a dark hole lies the singularity, where all the mass and energy of the dark hole, no matter how massive, are compressed into an infinitesimally small and dense point. The singularity has infinite density and gravity, which is both fascinating and challenging, as our understanding of physics begins to break down when we try to understand what occurs there. Scientists are still studying this mysterious region, hoping to uncover the secrets hidden within the hearts of dark holes. Dark holes form from the life cycles of massive stars. These stars are immense powerhouses fueled by nuclear fusion reactions in their cores, where hydrogen atoms combine to form helium, releasing vast amounts of energy. As long as the star has enough hydrogen fuel to continue fusion, it remains stable. However, once it exhausts its hydrogen, the star begins fusing heavier elements like helium, carbon, and oxygen. Each fusion reaction with heavier elements produces less energy, causing the star to burn through its fuel more quickly to maintain balance. Eventually, the star reaches a critical point where it can no longer fuse elements, and its core collapses under its own immense weight, forming a dark hole. Stars with masses less than about 3 times that of the Sun become white dwarfs instead of forming dark holes. These dense remnants of carbon and oxygen continue to emit light from residual heat. Stars with masses between about 3 and 10 times that of the Sun explode in a supernova, leaving behind a superdense ball called a neutron star. These neutron stars have masses up to 2 times that of the Sun, yet they are only about 10 kilometers in radius. Stars with masses greater than 10 times the Sun's mass collapse into dark holes, their cores contracting to zero volume and infinite density. Dark holes come in various types. Stellar mass dark holes form from massive stars at the end of their lives, typically with masses ranging from a few to several times that of the Sun. These are quite common in our universe and beyond. Supermassive dark holes, on the other hand, are astronomical giants with masses ranging from millions to billions of times that of the Sun. They are located at the centers of most large galaxies, including the Milky Way. These supermassive holes likely formed during the early universe from enormous clouds of gas and dust, or from mergers of smaller dark holes. Intermediate mass dark holes, sitting between stellar mass and supermassive dark holes, remain somewhat mysterious and are not as frequently observed. Researchers believe they may have formed from the collapse of extraordinarily massive stars in the early universe, or through the merger of stellar mass dark holes in dense star clusters. Primordial dark holes, which may be relics from the dawn of our universe, could have emerged from fluctuations in the density of matter and energy shortly after the Big Bang. These dark holes come in a wide range of sizes, from tiny to colossal, but their existence remains speculative, as they have yet to be directly observed. Dark holes can also rotate. Non-rotating dark holes are described by the Schwarzschild solution in Einstein's theory of general relativity, characterized by a spherical event horizon and a singularity at the center. Rotating dark holes, described by the Kerr solution, have an oblate event horizon and a ring-like singularity. Their rotation creates an ergosphere, a region where spacetime is dragged along by the spinning dark hole. Kerr-Newman dark holes, which both rotate and carry an electric charge, are described by the Kerr-Newman solution. The electric charge distorts their event horizon and singularity. Researchers have also discovered ultramassive dark holes, truly gigantic objects with masses exceeding 10 billion times that of the Sun. Using gravitational lensing, astronomers identified these colossal dark holes using a technique based on Einstein's general theory of relativity, which involves massive objects bending and distorting light. The Hubble Space Telescope observed an ultramassive dark hole in the Abell 121 cluster, located 2.7 billion light-years away. This dark hole has a mass around 30 billion times that of the Sun, continues to open new avenues for understanding their formation and evolution. Black holes remain some of the most intriguing and enigmatic objects in the universe. Their intense gravitational fields, event horizons, and singularities challenge our comprehension of physics. Recent discoveries, including ultramassive black holes, light bending around black holes, and wandering black holes, highlight the ongoing quest to uncover their mysteries. By focusing on these celestial phenomena, scientists push the boundaries of our knowledge, unveiling the secretive aspects of the universe. Black holes, often considered the most mysterious and awe-inspiring objects in the universe, captivate our imagination and challenge our understanding of fundamental physics and cosmology. These cosmic anomalies, where gravity is so strong that even light cannot escape, represent the extreme limits of our current scientific understanding. One of the most fascinating aspects of black holes is their formation. While we know that stellar mass black holes are born from the collapse of massive stars, the exact conditions and processes that lead to their creation are still under intense study. When a massive star exhausts its nuclear fuel, it can no longer support its outward radiation pressure against gravitational collapse. The star's core implodes, forming a singularity, a region of infinite density and gravity surrounded by the event horizon. Supermassive black holes, found at the centers of most galaxies, including our Milky Way, present an even greater mystery. These colossal objects can have masses ranging from millions to billions of times that of the Sun. Current theories suggest they may form through the gradual accumulation of gas and stars over cosmic time or through the mergers of smaller black holes in dense galactic centers. Intermediate mass black holes, which bridge the gap between stellar mass and supermassive black holes, are particularly elusive. While there is evidence for their existence, their formation mechanisms remain speculative. They may have formed from the direct collapse of massive stars, or through the merger of smaller black holes in densely populated star clusters. Another exciting possibility involves primordial black holes, hypothetical remnants from the early universe that could have formed shortly after the Big Bang from regions of extremely high density. If these primordial black holes exist, they could vary widely in mass, from tiny to very massive, and may even contribute to the mysterious dark matter that makes up a significant portion of the universe's mass. The study of black holes extends beyond their formation to their role in shaping galaxies and the larger universe. Supermassive black holes, for example, are thought to play a crucial role in galaxy evolution. Their gravitational influence can regulate star formation rates and shape the distribution of stars and gas within their host galaxies. Understanding how black holes evolve and interact with their environments is essential for deciphering the complex processes that drive astronomical evolution. One of the most significant aspects of black holes is their impact on spacetime itself. According to Einstein's general theory of relativity, the presence of mass and energy distorts the fabric of spacetime, creating what we perceive as gravity near a black hole. This curvature becomes so extreme that it distorts reality to an unprecedented degree. This phenomenon not only affects the movement of objects and light but also challenges our understanding of how the universe behaves on both the smallest and largest scales. The study of black holes has opened new possibilities for testing the fundamental laws of physics, particularly at the intersection of quantum mechanics and general relativity. Technological advancements in observational cosmology have revolutionized our ability to study black holes across the electromagnetic spectrum. Instruments like the Event Horizon Telescope (EHT), which captured the first direct image of a black hole's shadow in 2019, have provided unprecedented insights into the nature of these cosmic giants. By combining data from radio telescopes around the world, the EHT produced an image of the supermassive black hole at the center of the galaxy M87, confirming theoretical predictions and expanding our understanding of black hole structure. The dynamics of matter swirling around black holes, known as accretion disks, are also under intense investigation. As material spirals into a black hole's gravitational well, it heats up and emits radiation across the electromagnetic spectrum. Observing these emissions allows scientists to probe the properties of black holes and their surrounding environments, shedding light on the nature of spacetime and the physics of extreme gravity. Recent observations have also provided valuable insights into the role of magnetic fields in shaping black hole environments. Magnetic fields can influence the behavior of charged particles near black holes, structuring the accretion disks and generating powerful jets of particles that extend far into intergalactic space. Understanding how these magnetic fields interact with a black hole's gravitational fields is essential for comprehending the full range of their astrophysical effects. Black holes also serve as enormous laboratories for studying the behavior of matter under extreme conditions. Matter falling into a black hole can reach speeds approaching the speed of light and temperatures exceeding millions of degrees Kelvin. By observing X-ray and gamma-ray emissions from these hot ionized gases, astronomers can test particle physics models and explore the mechanisms behind high-energy radiation production in the universe. The discovery of gravitational waves by the Laser Interferometer Gravitational Wave Observatory, LIGO, and Virgo collaborations has opened yet another window into the study of black holes. These ripples in spacetime, caused by the mergers of black holes millions or billions of light-years away, provide direct evidence of events that were previously invisible to traditional telescopes. Gravitational wave astronomy promises to revolutionize our understanding of black hole populations, their growth rates, and their role in shaping the evolution of galaxies over cosmic time. Gravitational lensing allows scientists to observe and study objects that are too faint or obscured by measuring the bending and magnification of light caused by massive objects. This technique helps estimate the mass and location of such objects. One notable application of this method was the discovery of the ultramassive black hole, which provides new challenges for understanding black hole formation and evolution. It suggests that black holes could form through rapid accumulation of matter or dramatic collisions with other black holes. This discovery also offers a chance to test Einstein's theory of relativity under extreme conditions, as well as explore the nature of dark matter. Dark matter makes up a significant portion of the universe's mass, and studying ultramassive black holes can reveal insights into its elusive properties. Gravitational lensing, which causes optical illusions when large objects bend light, allows us to study distant phenomena like black holes. There are various forms of gravitational lensing. Weak lensing subtly alters the shapes and positions of distant galaxies, providing information about dark matter distribution. Strong lensing creates dramatic effects such as multiple images or arcs of light around a lensing object, helping researchers measure its mass and shape. And microlensing, caused by smaller objects like stars or planets, briefly magnifies background stars, aiding in the discovery of exoplanets and other celestial objects. In a groundbreaking observation, Scientists detected light from behind a black hole using telescopes like the European Space Agency's XMM Newton and NASA's NuSTAR. They observed X-ray flares from an ultramassive black hole located 800 million light-years away. As gas fell into the black hole, it heated to extreme temperatures, forming a glowing corona. Some of the X-ray flares were reflected by gas behind the black hole and bent by its immense gravity and magnetic fields, making them visible to us. This observation confirms Einstein's prediction that gravity can bend light. The discovery, made over several years and reported in 2018, revealed X-ray flares with distinct colors and delayed appearances. These flares, light echoes from behind the black hole, support the concept that gravity bends the fabric of space, allowing light to curve around massive objects, a phenomenon known as gravitational lensing. The study also highlights the role of magnetic fields and extends our understanding of black holes, their coronas, magnetic fields, and accretion disks. In another remarkable discovery, astronomers found a wandering black hole using the Hubble Space Telescope and gravitational microlensing. This black hole, located about 5,000 light-years away, has a mass about 3 times that of the Sun and moves at 45 kilometers per second. It likely formed from a massive star that underwent a dramatic collapse and was ejected into the Milky Way by a supernova explosion. The discovery sheds light on the vast journeys of such objects and their interactions with their surroundings. The black hole's strong gravity bent the light of a background star, revealing its presence. This highlights the importance of gravitational microlensing in studying isolated black holes and other interesting cosmic objects. Wandering black holes, born from stellar deaths, roam through the universe, and there may be millions of these rogue black holes in our galaxy alone. Their discovery challenges our understanding of their development and behavior, offering insights into the final stages of massive stars. In November 2022, astronomers found the closest black hole to Earth, named GB1, located about 1,566 light-years away in the constellation Ophiuchus. This black hole, 10 times the mass of the Sun, is part of a binary system with a Sun-like star. It was identified by observing the star's wobble caused by the black hole's gravitational pull. This discovery challenges our understanding of black hole formation and binary systems. GB1's proximity offers a unique opportunity to study the effects of a black hole on its companion star, providing new insights into their interactions and the dynamics of binary systems.